Okay, if we're going to study user interfaces, the first thing we need to understand is the human vision system, because this is the primary way we get information into our human being. To understand that, we start with the anatomy of the eye. Now, from high school biology class, we know that we have a lens, which performs the focusing, and it focuses on the retina, which consists of a huge number of sensors. And then we use the iris, which controls how much light gets into the eye. For most of our discussion, we're going to focus on what the retina does for us and its characteristics. But first, let's talk about how much light gets into the eye through this opening, which is your pupil. Alright, so we have the iris. It opens and shuts depending, so if there's very little light, this opens up wide, lets a lot of light in. If it's really bright outside, this narrows down tight. It's only a little light in. The reason is because we only have so much sensitivity in our retina. So each individual sensor on this retina here, each of these millions of sensors, can sense 64 levels. Now what that means is if you let too much light in, it gets completely saturated and all you see is bright. All you see is bright because it's going way over the capacity of each of these individual sensors. If you don't let enough light in, then all you see is gray or black because there's not enough light to actually excite the sensors. That's what the iris is doing for us. Open and close the pupil to control how much light gets in. Now, since there's only 64 levels on each of these sensors, if you do a little bit of math, you figure out that you only need 6 bits to store that. Now we usually use 8 bits, mainly because 8 bits forms a nice byte and it's easy to compute with. But you only really need 6 bits to take care of what the retina can actually sense. So 6 bits on each sensor, that'll give us enough to duplicate what the retina can actually sense. Okay, now to understand a little bit what goes on with that iris, over here on the left hand side we have a Kindle. Both of these pictures are outdoors. If you notice, this one, the image is really dark. Now it turns out if you take it inside, it looks really bright, and here's why. When we set the image on a standard screen like this one, like you'd find on your iPhone or your iPad or your Android tablet, any of those, when we set the brightness on here, that stays pretty much at constant brightness. The problem is when we go outside, it's really super bright out there because of the sun. Now our eye handles that by closing down the iris. Take the iris, close down the pupil. See, look out here. When we're not looking at this, if you look out here, this is actually pretty bright outside. In fact, we're letting too much light in, and notice these are all washed out. Our iris is trying to compensate. I'm looking at this, says I'm not getting enough light. I really can't pick that up, but I've got all this brightness around here, and when I have all this brightness to protect the retina, I'm going to shut down. So the iris shuts down, lets very little light in, makes this thing look dark outside. Now the Kindle is different. This is actually generating light. This display is using digital electronic paper. Electronic paper controls the reflectance of light. The battery in this Kindle does not generate any light at all. All it does is switch these little pixels so that they reflect light. So when I'm outside, it reflects a lot of light. When I'm inside, it reflects a little bit of light. So that's why this device claims to do so much better outside than this device. It's all about trying to manage your retina. When you're outside, that retina will shut down, which means it won't take in enough light to see these kinds of screens. Okay. In our retina, there are 2 areas that are important to us. The biggest area by far is what we call the periphery. That's all this area right down here. And then there's this little area right here. It's not very big. It's called the macula or the fovea. Okay, it's not very big, but there's some interesting things about this. First thing is the kinds of sensors. So out here in the periphery, virtually all of the sensors are the type we call rods. All rods can do is they can detect gray levels. They cannot detect color. Everything looks gray. It's just bright or dark, or 64 levels in between bright or dark. That's the rods, and that's all this area out here. This is the periphery. Okay? Now right here in the macula, the fovea, we have cones. Cones can sense color. So this is where all of our color vision is located, right here in this little tiny spot. Now, the proportion between rods and cones and the different kinds of cones is really important in understanding what goes on. So, there are 20 rods to every cone. Wow, we got lots and lots and lots of grayscale sensing. However, those 20 rods are scattered. Actually, they're 20 million rods. They're scattered over a very large area. Because these rods cover such a large area, their density is actually quite low. Now, inside this little fovea area here where all the cones are, so even there's only one cone to every 20 rods, they're all crammed into this little tiny space right here, which means the resolution is really, really high. This is where we read. This is where we study, right here. This is where we sense other things, like, is a rock going to hit me in the head? Or where did I put my hammer? That's the kind of things we sense out here. Okay, now the other thing we need is we've got 3 kinds of cones. The type of cones vary based on the pigment that's behind them. So for red cones, that's 64% of all cones. More than half of our color sensing is red. 33% is green, and blue is this really small 3%. Okay. Now when you look at things, it looks like red, green, and blue are balanced, so you see white. And the reason is because your brain is boosting the importance of these. But because there's not very many, the resolution of your eye is much better on red things. You can see more detail in red than you can see in blue. Okay, that will also have an impact on how we use color. So we're going to study color models later, red, green, and blue. This is where it comes from, the types of cones. We'll come back to them. The key thing to remember, more than half are red, a lot of green, almost no blue, and the rods, which cover this huge amount of area, are all gray. Okay, so here's a picture of Benjamin Franklin. It looks like it's all in color to us. This is what you think you're seeing. However, remember our rods and cones. We actually only see color in a little tiny spot. We only see color over here in the fovea. We don't actually see color everywhere. So what your eye actually sees is this. Okay, if your eye is focused right now on Ben's eye, you'll see the fine detail in the corner of that eye, and you'll see it in color. The rest of the eye, out here that's being sensed by the periphery, you're going to see in low resolution because the sensors per inch is low, and you're going to see it all in gray because rods can't sense color. Okay, now most of you say, but that isn't what I saw of Ben Franklin. I saw Ben Franklin of all in detail. Why is that so? Okay, so here's Ben Franklin again in all of his resolution and in all of his color. And here's what's going on in your eye. Your eye is moving. It moves continuously. It virtually never stops. And you actually, if you have to concentrate to make it stop. So what it's doing is it's scanning across this picture of Ben and remembering all of the color and all of the detail. And if it starts to forget some of that color and detail, it just zooms that eye back, the fovea right back there. So the reason you think you see in detail is every time you want to think about a particular detail, like his nose or the other eye, your eyes automatically jump to that point. Every time you think about concentrating on something, your eyes automatically jump to that point. Now, this jumping around of the eye is called the saccade. And the saccade happens every 200 milliseconds. Okay, so what's going on here is 5 times a second your eye is jumping around, moving from place to place, studying this picture of Benjamin Franklin, trying to make sense out of it all and remembering what's going on. Now the other thing you're thinking is, I see Ben completely in color, but you're telling me that most of it's in black and white. Well, it turns out you're actually remembering the color. You're not actually seeing the color. You're remembering the color from the last time your eye was there. Now what keeps this all organized correctly is the periphery. Because the periphery, even though it's lower resolution, I know where his head is, I know where his eyes are, I know where his chin's going to be. There's his collar, there's his shoulders. So the periphery is helping me target. So every time I think about I want to see his ear, it's right there. I know it's right there. So my eye, my fovea instantly jumps to the part and I can study his ear if that's what I want to do. Okay. So let's think about an experiment here on the nature of the macula. What I want you to do, you probably want to pause this right after you look at this. I want you to get a piece of text out of a book, out of a paper, out of anything, just a paragraph of text. Then I want you to focus on one word of that text. Focus your eyes right on one word of that text. And then do not move your eyes, but try to read the words above and below. You'll find that it's virtually impossible to read those words above and below or to the left or the right without moving your eyes. Now, normally what you do is you would just let your eyes jump and move, and you'd be able to see any word you wanted to see. But if you hold your eyes still, you find out that that macula is not actually very big. And you need that macula to be able to read or study or do fine detail. Okay, so stop right now. Do that experiment before you go on. All right, let's summarize what we did here. The periphery versus the macula. The macula over here, careful close study, it's very slow. You've got a little tiny window. You can move that window around 5 times a second very naturally, and you can see color. The periphery only sees gray because of the rods, and it's blurry because they're spread out over such a large area. But it allows for fast targeting. I can actually see an entire range and know where the ear is or the eye is or the nose is, and then take my macula over to that location. So here's what this means for building user interfaces. If you are going to require your user to find things by reading and carefully studying them, you're going to have to use the macula and the saccade. That's the only place that'll give you that resolution, and it's going to be slow. Little tiny window, 5 times a second. However, if you organize your user interface so you can find things rapidly with the periphery, it's going to be gray, it's going to be blurry, but if you can do it, it's going to be very fast. So, quick review of the eye. The lens for the focus, the iris controlling how much light gets in, the retina, 64 levels. Part of the retina is periphery, which has grayscale rods spread out over it, and a little tiny part of the retina is the macula or the fovea, has all the color sensing. That's how the eye works. We're going to refer back to these facts over and over and over again because they're going to control how we think about what our users can see. If you understand this, the periphery, the macula, what they can see, rods, cones, then all the other things we talk about will make a lot more sense. Good luck. We'll see you in the next video.